Good afternoon. I'm Michael Hall, one of the grazing specialists here at the National Technology Support Center. Our presenter today is Craig Runyon, recently retired from New Mexico State after 29 years of public service as an Extension Water Resources Specialist. Craig represented New Mexico State University as foreign manager on international projects in Yemen, Ukraine, and Uzbekistan for 7 years, in addition to his work at New Mexico State. As emeritus professor, Craig coordinates the annual Windmill Technology Workshop at New Mexico State University, and I'm sure he'll tell us a little bit more about the workshop, which is coming up at the end of this month. Since his retirement, he and his wife, Marcia, have started a commercial windmill and solar pump business out there, so she's going to keep him tied up and working probably more than he was doing as a professor there at New Mexico State. Craig and I met in 2010, one sunny, wet day at a forward operating base, Shank, in Afghanistan. While he was involved with New Mexico State Afghan Water, Agriculture, and Technology Transfer Project. It was a USAID-funded project working with the Afghan Ministry of Agriculture, Irrigation, and Livestock. And with that, Craig, I'll transfer over to you.
Good afternoon, everyone. Good morning to some of you. It looks like we have a really good turnout for this afternoon's webinar. I might have worn a tie if I had known so many people were going to show up for this. My name's Craig Runyon. Thank you to Mike for that nice introduction. I'm sitting in Las Cruces, New Mexico, near the banks of the Rio Grande, and I'm in the local NRCS office with my local host. Adrian Tafoya is the DC here in Doña Ana County, and my wife is helping me with this confusing screen. Marcia Wright is here with us also. Mike mentioned our annual windmill school I've been a part of for several years, and it's something that I enjoy doing. We have a really good workshop each year. This is the 38th annual NMSU Technology Certification Workshop coming up at the end of May. We try to teach our students everything from initial how to select a windmill for water pumping to complete construction and erection. So if you have any interest or know of anyone who has any interest in learning more about conventional windmills and putting them up, Dr. Carlos Rosenkranz is my partner, and he's the one that would help you get more information about the workshop. So the windmill you see in the picture is not the type of windmill we're going to be talking about today. The old world, ancient windmills that we historically have seen around the globe probably date back to as much as 1,000 years BC. There's evidence that harnessing the winds to do work goes back at least that far, and who knows, maybe even further. Try to move on here. Let's see. I have actually had the opportunity to visit that windmill in Holland that you saw the picture of a couple of times, and it's impressive if you ever get a chance to visit one of these old world windmills. It's very awesome, the work that they made those old mills do, from sawmills to grist mills. You name it, they could find a way to make that wind do the work for them. But it wasn't until the late 1800s that the modern conventional windmill was developed here in the U.S., and it sort of went side by side with the development of well drilling. As well drilling, or in some cases even well digging, was improved, then there was an obvious need for a better windmill, something better than the windmills that had been around for so long. The wooden mills, the canvas mills, there was a recognized need for something more efficient. And the steel windmill, the steel-bladed windmill that we have today, was designed around 1880 to 1900, and really became popular right at the turn of the 1900s, turn of the century. That particular windmill that we see today was some 75–80% more efficient than what had previously been used for water pumping, and essentially has been unchanged in the past 120 plus years. It's the same windmill we use today, and it's hard to improve upon it. Now, it's kind of hard to talk about windmills for water pumping unless we talk about what it is we're getting water from. So this is one of the first things that a miller would look at is the well, and certainly something that's critical to being able to get the mill to perform for you is you have to have a good well. For the uninitiated, and I don't want to insult anybody's intelligence, basically a well is just a hole in the ground with a straw stuck in it, and that being a highly technical sort of industry, I'm not a driller. We just get to come along and compliment or curse the drillers that leave the well behind them. But what we look for is a very well-constructed well that's going to serve for many, many years. If the well driller knows what he's doing, there's no reason that well should not be there indefinitely, notwithstanding the water that comes through it. And a good well design, well constructed, will ensure years and years of life, a good security against pollution, and hopefully good water for as long as you need to use that well. Having been in extension and worked with water quality programs and pollution prevention programs, I'm somewhat sensitive, and I know we're all aware of it today, is what you need to do for your well in order to keep its integrity and to keep it safe, and the water that you draw from it safe. And some of those particular hints listed on the screen right there, one of the most important is to have that well separated from any risky land use activities. In other words, livestock pens, septic tanks, oil pits, or something that would cause any concern or risk to the groundwater below surface. And I should have listed this on my slide, but one of the most valuable resources that you can find for good well maintenance and protection is called the Pharmacist program. Most of you have it in your state. It's a self-assessment program where a well owner can go and assess the risks located around their own private well, and is used for other types of wells, municipal wells, otherwise. But where we're dealing so much with source water protection and the environmental concerns for protecting our groundwater, which belongs to all of us, then some of these issues become somewhat critical, and there is really quite a bit we can do toward protecting that groundwater. So here's an illustration, a kind of a cutaway of what a good well construction would look like. These are practices that have to be implemented by the driller. And for those who are able to deal with their driller prior to getting the drill weld, there should be some dialogue. There should be some discussion, and based on local regulatory practices and the reputation of the driller, you can have a well drilled that will be safe and provide water for a long time to come. Some of the basics, though, are the casing should be strong, usually steel, sometimes plastic, PVC casing. It should penetrate the water table sufficiently to avoid any future problems in the event the water table should drop. It should be screened. Oftentimes you find an open hole at the bottom of that, just an open bore at the bottom of that casing. One of the things on top or toward the surface is that it should be grouted around and a pad built around the casing at grade on the surface. That goes a long ways toward protecting any inflow into the well that might contaminate the water. There are local and state regulations regarding a lot of this. In New Mexico, for example, the grouting is not required. It's optional. And so we try to encourage our drillers to include that grouting and get that casing fitted in well into the borehole. One of the things that have to be avoided is the interspace between the borehole and the casing not being well sealed. Lateral groundwater movement toward that casing could provide a big risk to your groundwater if that seal between the casing and the earth is not well made. So that's something you want to pay attention to. But that's sort of my extension soapbox, and we like to see our well owners pay attention to some of these issues. Water quality testing, of course, most of you know about. Recommended once a year. If you have problems, maybe more frequently. But if you know there's a problem with the well, try to locate the source and deal with it. And then proper abandonment if the well's not going to be used for more than 3 years. Here in the West, most states say if it hasn't been used in 3 years, it is considered abandoned. So know what your local statutes say and take care of your water. Okay, changing topics just a little bit. We find today with looking for alternative energy sources for pumping water that a lot of people are deciding, should I go solar PV panels or should I go conventional windmill? I might preface some of this by saying that a lot of the people who are considering windmills think that they might also get electric generation off of that windmill as well as water pumping. And our basic response to that is water and electricity do not mix. And there is nothing available on the market today that will do both jobs. You can get a wind generator or you can get a windmill for water pumping, but you cannot find something that does both. The technology is not there yet. Perhaps someday it will be, but we're talking just water pumping windmills. So for those interested in solar or comparing what they want to do with solar and or wind, we put this up to look at some cost comparisons. On the left side of the slide, you'll see a very typical setup, and this is a 4-inch well, considered a domestic well, one that you'd have at your residence. Assume that the depth of the well is 100 feet. Water table can be found at about 30 feet deep, and so we're going to place the pump at about 50 feet deep and give you about 20 feet of water over your pump. Your typical solar setup would look something like this. A 3-inch pump will fit into a 4-inch casing, and something like a 36-volt, more or less, and I put dual AC and DC pump at a price of $1,400. Now, there are DC pumps available on the market for much, much cheaper than this. But you know, this is an AC, DC, dual voltage pump, and the technology for these pumps is such that you can plug it into 110, you can put a 220 in it, or you can run it off a solar PV panel. For those individuals who care about being able to get water out of the well, this technology is invaluable. For days and days of cloudy weather, when your solar energy is not working for you, you can literally plug that pump into a 110 circuit and get water out of it. Or you could take a generator to the wellhead if it's a remote well and start your generator and plug it into it. Now, if you need the water from the well, there's really no alternative but to get a pump that will pump no matter what you throw at it. And these literally will pump from 36 volts to 250 volts. It reads what it is being asked to do, and the control panel, which is also pricey, will interpret that voltage and give you the most efficient delivery of water. But if that's not important to you, you can cut that pump price down probably by more than half. Obviously, it needs the PV panels, and for this example, 270-watt panels, there's a substantial cost. The panel mounting rack, if you can weld, you can probably eliminate that cost. And the 60 inches of 1 1/4-inch poly pipe is about 55 feet short of what it should be. I meant to put 60 feet there, not 60 inches. So at about $1 a foot, you can get the pipe to go down the hole. Poly pipe is nice when you're dealing with these solar installations. Usually, even with a 60-foot, 50-foot drop, 60-foot drop, you're looking at a one-man job. One person tie the pump to the end of that poly tube, and you can just literally feed it down by hand and have it installed. So for something less than $5,000, and that would vary across the country, you can be set up and pump with solar energy. Now compare that to the right side of the slide there, and this again is a very typical setup. We see 85% of our windmill configurations look just like this: an 8-foot diameter wheel on the windmill, about $3,000 list price, 27-foot tower, $2,800. And why a 27-foot tower? You can get towers or build towers that are 21 feet or 16 feet or however tall you want them. But I might ask the audience, just go ahead and send a note in, why do you think the 27-foot tower is the most conventional and the most popular kind of tower? There we've got 60 feet of 2-inch galvanized pipe, very expensive. 2-inch galvanized and bigger is by the foot, is not cheap. Now you can use PVC, but you have to be careful to use a Schedule 80 PVC, thick-walled, that is threaded and not glued, because this pipe has to go down the hole one joint at a time. So and then sometimes it has to come out of the hole. So glue is not reliable and not advisable for a lot of these types of installations, whether it's solar or wind. But but a threaded Schedule 80 PVC is used fairly often. Personally, I don't like them because I think the PVC ages and will begin to crack, and there's some vibration in the whole apparatus that PVC does not like. The 1 7/8 inch cylinder is used on the 2-inch galvanized pipe for servicing purposes, and then the stuffing box. Many of you may not know the stuffing box. It works sort of like a pitless adapter in that it will divert the water laterally at the surface, so that water doesn't just shoot up the pipe. You can plumb in a diversion and then send the water to where its demand is. So $6,700 compared to less than $5,000 for solar, and that the cost of these installations are important to a lot of people. But let's move to the next slide and compare the performance of these things. Same setup, same conventional scenario that we have. With the solar, this is working on potential performance of these two different sorts of water pumping. Solar performance potential with a 300 plus or minus watt. We had two 170 panels, about 6.5 gallons per minute on a bright, sunny moment. Average 8 hours per day of solar radiation sufficient enough to drive the pump, and 8 hours a day, depending on what part of the country you live in, may be more than you get. It just depends. Sometimes in the middle of the summer, we wish we only had 8 hours in New Mexico, because by about 5 in the evening, it's pretty darn hot out here. But if you have it, you can realize as much as 6.5 gallons a minute with that setup. So 60 minutes times 8 hours, 60 minutes in an hour times 8 hours of potential pumping per day is something more than 3,000 gallons of water per day. Now, if you look at the windmill performance potential with the 1 7/8 cylinder that we're putting down there at 50 feet, we get 3 gallons per minute, quite a bit less than half of the solar performance, but with an average 15 to 20 mile an hour wind, we have the potential for doing it 24/7. We don't have to rely on the sun to be able to provide the power to the pump. So, with that in mind, and realizing that we can get wind anytime in a 24-hour period, we can potentially pump a lot more water than you could with the solar system. 4320 or more than 4,000 gallons per day, and that might be important for filling up a livestock tank or supplying water to a domestic supply tank, storage tank. That could be an important difference. Some of the considerations for solar is know what your local regional solar radiation potential is, and be careful when I say seasonal that you don't have shorter days during a period of the year when you need most water. It's got to match. It's got to match the needs here. With a solar pump, if you have less sun, you're going to get less water pumping. If you have more sun, you're not going to realize any more out of the pump than it's designed to deliver. That it has a built-in limiter or limitation with its design that will only deliver so much water. And one of the things that we deal with a lot in the West, not only in New Mexico, but in a lot of areas where we have multiple use public lands, is PV panel damage, primarily from vandalism. People like to shoot at things, throw rocks at things, or whatever. And that one 30-30 shell through a PV panel is a couple $1,000 or almost $1,000. And then the other thing too is the water quality. If you have substantial total suspended solids in your water, these pumps don't tolerate it very well. There are some pumps that are rebuildable, and some of the pumps on market today address the sand and suspended solids better than other pumps, but it's still a problem. Not so much of a problem with a windmill pumping cylinder. Then the considerations for windmill are the wind speed. Know that you've got wind speed. In the West, we have wind all year long except when we need the water most. That's July and August when the livestock need the water. We have the least wind. And so as a result, our ranchers and animal operations who use windmills have to have very large storage capacity to get through about 8 weeks of no wind. And with more wind, you get more water out of a windmill, because with a windmill, you're getting a positive displacement with every stroke of every turn of the wheel, every stroke of the plunger, you get that much more water. So up to almost hurricane strength winds, we can get more and more water as the wind blows harder and harder, and that fills up our storage tanks. One thing that we're seeing more and more of today is people want to see an AC electric submersible as a backup system down the well with the windmill cylinder, and that's easily done. We've done several of them where we just take a fairly inexpensive electric AC submersible pump and put it on the bottom of the windmill cylinder and run the cable out the top of the hole, ready to be used when the well owner needs it. And otherwise, it's just sitting there. As long as the windmill is pumping, water will pump right through that submersible. Just open the check valves in that submersible and right up the well pipe. And then the last consideration, and this may be a personal note, is that they are therapeutic to watch turning. We have windmills in the West that we just love to watch turn. And I have a mentor in the windmilling business who really could not start his day unless he knew his windmill was turning. And if there was no wind and it wasn't turning well, he was always late for work. Okay, this is not so much important as to how a windmill works, but one thing that is critical to anybody interested in working with windmills or even working near windmills is the safety consideration. We take this seriously. There's a lot of risks involved, even on the ground, working on the ground with steel overhead and cranes in motion and whatnot. This is an important issue and one that we emphasize with, certainly in our school and with all our colleagues, is don't take it lightly. We don't like accidents on these windmills, and the wind is unpredictable. When you're on these towers, you have to expect the worst is going to happen. So fall protection, tie-on protection, everything you can do is probably not enough to provide your own safety. Okay, basic operation. This is a typical windmill setup. You've seen the steel towers, or in many cases wooden towers. We see a lot of still. The tower has a couple functions. One is that it raises the wheel and the motor, the fan, if you will, above the obstructions around the ground. say that it should be some 20 feet or so above any obstructions that are something like 100-foot radius. Oh, okay. We've got an answer to the question about why most towers are 27 feet. An individual says can be reached with a standard ladder for maintenance. Actually, no, that's not it. It's a matter of convenience. The 27-foot tower is there to help you put 20 and 21 joints of pipe in the ground. The pipe has to go inside the tower before it can go down the hole. And if you've got too short a tower, you've got a problem, unless you want to go to the expense of cutting that pipe and threading it to fit inside the tower. We like to see 27-foot towers. That gives you room for apparatus, pulleys, and hooks at the top of the tower, and be able to use 20-foot joints of pipe and sucker rod, as you'll see here in a minute. The other point of the tower is that it has to be centered, and it really needs to be dead centered over the well casing. It's somewhat critical to the longevity and good installation of the windmill that the center of the tower at the top is plumb over the center of the casing in the well. If it's not the end of the world. It will still pump, but there are points at which the mill will rub and wear faster than you want it to. If it's dead level and plumb over the well casing and everything is operating as it's built to and as it's intended to, these setups can go 50 years or more with very, very little maintenance. Even like an annual maintenance is really that's all required. But where they're not level, where they're not plumb, and there's rods or steel rubbing on casings and whatnot, then they will wear and they will start to leak oil and that sort of thing, and won't last as long as they are really able to last. So the motor, what we call the motor of the windmill, which is the gear part of it, is the wheels driven by the wind. The individual sails of the wind are scientifically designed for the most efficient catchment of the wind, and that drives a shaft that has what we call pinion and bull gears attached to it. Basically, the design is not unlike any sprocket design or pulley design where you have a small drive gear and a larger driven gear. Smaller drive gear, larger driven gear will give you more torque and deliver more power to where you're sending it. And in this case, where we're sending it is to a pitman arm. And that pitman arm is just like an arm that's moving up and down. And in the case of windmills, it carries a plunger rod that extends from the motor all the way into the well. The plunger rod is attached at the bottom of the well to a valve that is responsible for lifting the water, and we'll see more about that here in a minute. One individual is asking, what about concerns with birds? The birds love windmills. They especially like the platforms that they can build nests on, and we see eagles and owls and everything else. But as far as flying into it, no. These are lower to the ground than what you're thinking of as electric generation windmills. The big setups that we see, the modern generation mills. These are not an issue with our birds. They have plenty of time to move around them. I've never seen it be a problem. Okay, main components the windmill. The wheel and motor, as I've mentioned, are on top. The wheel and motor are designed so that it has a dampening effect, so that the tail will help move the wheel out of the wind. I said earlier these things will operate in gale force winds, and they literally will, because they have this dampening effect that with a spring-loaded arm, the tail of the windmill will turn the fan out of the wind to prevent it from damaging itself. It's a wonderful feature where we can leave these things turned on without worrying about them flying off the top of the tower. They don't do that. It would take, and I'm not exaggerating, it would really take gale force winds to cause any damage to these things as long as they're anchored well in the ground. We've seen them actually survive tornadoes and come through with no scratches. The tower, and well, let me back up a little bit. The wood rod that is essential on all of the windmills is a device that's used as sort of a weak link or shear pin. The wood rod is that connection point immediately below the wheel and the motor that is used in the event that anything wrong happens below ground or above ground, for that matter, that causes an obstruction. The wood rod on the windmill is designed with specific measurements to break and shatter before any damage is caused to the pumping cylinder or the motor gears or anything else. That rod will break and the mill will no longer be connected to anything. So it can turn and spin and do whatever it wants, and it's not tied to anything at that point once the wood rod has served its purpose and breaks. And one of the things I forgot or I failed to put on here is that many of you interested in windmills might be in areas where winter freezing is an issue. That wood rod is that point which would prevent any buildup in ice in your well pipe from causing damage once the wind comes back. If it lays idle with no wind and the water should freeze, and then the wind comes up, you've got to deal with the ice. The wood rod is that weak link that will prevent any damage from occurring. That being said, there are things that can be done to prevent the water from ever freezing in the first place. What we like to see done, and even here in northern New Mexico where we get some pretty cold weather, just below the frost line in the well pipe that's supplying the water, we drill a very small, like about a 1/8 inch hole in the well pipe. We call that the weep hole. So when the wind quits turning and the water stops lifting and it's just sitting there, the water above the freeze line will weep out of the weep hole and empty the pipe and prevent any freezing. So then it will operate the next time the wind starts up again. So the connecting rods down the well, those are typically called sucker rods. That's what most people call them. The sucker rods have tied the wood rod, or the motor actually, to the cylinder, the pumping cylinder that's located all the way down into the water table. The pump cylinder, or the cylinder as we call it, does not actually pump, it lifts. It's not a rotary device, it just lifts water, and it lifts water one stroke at a time. Okay, tower assembly. Towers can be built on the ground and lifted, or they can be built one section at a time as you go up. Minimum 27-foot tower for handling full-length joints of pipe. It gets pretty expensive to cut and thread pipe to fit in anything shorter, so the price is is a no-brainer. Towers built on the ground can be just lifted with a hoist if one's available, if you can get one to the site. And they can be done by hand if you have enough manpower. There's all sorts of methods and techniques for lifting these up just using ropes and cables and some simple safety and a lot of people. One of the best ways to do it, if you know you're going to put a windmill up, is to build something like we see right here, where the bottom of the tower legs are actually bolted down to the pad, to the concrete pad, before it's ever lifted. And so all you're really doing is tilting up the tower, and in most cases it can be done with the motor and the wheel already on. So once it stands up, it's done. All you got to do then is do the well work, the downhole stuff. Very good way to do it, very safe, highly recommended. Here's where we plumb and level. Once that tower is up, then scooting it around back and forth using a plumb bob to get it right center over the well. If you spend the extra time to do this, your windmill will pump without problem indefinitely for a lifetime or more. Here's building the wheel and the tail before put on after the tower is set up, and this can be done fairly well if you've got a small A-frame, or even find some way to hang it up in the rafters of your barn or something. This little mill is not that heavy, maybe 300-400 pounds. I don't remember the weight of them, but they're not that heavy. And with the wheel on there, total weight of that thing is not something that you can't deal with. They're cumbersome, obviously, but they're not really that heavy. And here's where that motor would fasten onto the tower. This is what we call the stub tower. That threaded nut is removed, the motor slips right on, and you just bolt it right back on there. This is easily done on the ground. It's easily done in the air if you've got a way to lift that motor up too. Windmill builds the column of water connected with the plunger rod into the ground at the cylinder. It builds a column of water one stroke at a time up the well pipe. It's ratcheted up every time the wheel turns. It causes an upstroke and a downstroke on the plunger, and that's what lifts the water up the column. You see the water column here coming from the cylinder at the bottom of the well pipe, lifted one stroke at a time until it reaches a point of diversion, and a lot of times what we call this just a tank pipe or a drain pipe. If you use the stuffing box that I mentioned earlier, then you can divert it and send it even higher than the windmill itself. These windmills are capable of lifting water literally hundreds of feet. The deepest we could lift, or with the most head, I should say, we could lift, is somewhere around 1,000 feet elevation. So with a proper apparatus, that being a stuffing box, on top of the well pipe, we can lift this water up several hundred feet above the height of the windmill itself. This common setup in the West, where we've got hills and mountains, and we've got livestock tanks at the tops of those hills and mountains, we have to be able to pump water up the hill. And the hydraulics of it is that incline adds to your head pressure. Declines take away from that head pressure. So if you're going downhill, it's a gain. If you're going uphill, it's a cost. But being able to pump 400, 500, 700 feet elevation higher than the windmill is a great advantage if you decide to use the stuffing box. Here's the stuffing box right here. Screws in to the bottom, or actually I should say to a fitting that would be a T-fitting, screws into the top of the T-fitting and prevents water from going out the top of the well pipe. And below that, at the T-fitting, you have a lateral diversion, and you can send water anywhere you want to send it. Cylinder pump is the heart of the system. It ratchets and lifts water repeatedly back and forth. It consists of a top plunger and a check valve, a bottom check here, and simple operation is pressure from the water column in the pipe, that's water trying to go back down, causes the plunger valve to close. It just seals the plunger valve. And as the upstroke of the windmill pulls that plunger up, it lifts water the distance of the windmill stroke, which is variable. Water rises up the column and goes into its diversion point. Negative pressure within the cylinder, because it's lifting that water, will open the bottom check valve and allow the groundwater pressure to force water into the cylinder. So then on the downstroke, the top plunger valve opens and passes through that trapped water in the cylinder, and the bottom valve, check valve, closes and prevents that water from flowing out of the cylinder. And once the plunger reaches bottom dead center, you're ready for a whole new stroke, a whole new upstroke. And that's what's meant by every time it reaches bottom dead center, a new bottom of the water column is established. Here's a more graphic illustration. You see the check valves, the yellow balls, on the left-hand side with both valves closed when there's no wind blowing. Those valves will hold the water in the well pipe, hold the column of water, so that as soon as the wind starts turning, water's right at the top of the surface and ready to start flowing. On the upstroke, the plunger valve is closed and the check valve is open, lifting water up the column and bringing water into the cylinder as the plunger rises. The downstroke plunger is open so that it can pass through the newly trapped water in the cylinder, and the bottom check valve is closed so that water can't flow back into the ground. Here's it idle. Upstroke starting, valves in their appropriate position, plunger closed, check valve open. Plunger still closed. This is top dead center right here. That's as high as the plunger will rise. That's its stroke. Downstroke begins. Top plunger opens. The bottom check valve closes and traps the water from flowing out. Almost bottom dead center here, and you're ready for a new stroke to begin. One stroke at a time. That's how it's done. Now, for those working on mills, and you have seen these maybe with your well drillers or plumbers who work on wells, some of these tools are fairly simple, easily shop fabricated. I think we've built all but this bottom one, the black hook-looking thing, which is called a rod elevator, commercially made, but not essential. You can build something. All of these are shop-made, just simple devices used for working the pipe and working the sucker rod. And if you give it a little thought, you could probably come up with something better than we have here. Important thing is, I made a note here, always use a swivel hook. When you're using a cable, even on a crane or a boom, always use a swivel hook, because once it passes below the surface, you have no idea what's going on down in the hole. And they spin and ratchet and spiral around, and if you don't have a swivel hook on there, you can find yourself in trouble. Okay, here's a picture of the plunger on the sucker rod, and it's about to go down into the well pipe, which is in the hole, already installed. It fits into the cylinder once all the sucker rod is in there. Final steps, if you're using the stuffing box, final connections will be made to cut the sucker rod to fit the packer head. And with the mill at bottom dead center, you need to know where the stroke of that thing is that's when you hook up your wood rod. Wood rod is also convenient because it's easily cut, doesn't have to be threaded, and it fits into a prescribed point on the sucker rod that will make your final connection. These are somewhat important steps that we don't have time to dwell on, but if you're interested in doing this or know somebody who is, there is a manual called the 702 Windmill. I didn't make a note of it in my slides. The 702 Windmill is the name of the book, and it is written by Dr. T. Lindsay Baker. If you have any interest in looking at some of the practices involved with what we've talked about here this afternoon, I highly recommend that book. T. Lindsay Baker, the 702 Windmill. Dr. Baker didn't seem to have a whole lot more to do than write about his passion, and that's windmills. And it is the most comprehensive how-to book on conventional windmill water pumping. This is the windmill that Sergeant Major Hall was partly responsible for getting put up in Afghanistan, and it's a pretty cool picture. Please contact us for more information if you have any interest or want to know more about windmills. We're available. My contact information there. Email me or call. Happy to visit with you. I love talking about windmills, and that's all I have today.
Thank you, Craig. We had two questions that came in. One was, how easy is it to replace the wood shear pin that you talked about?
Good question. It is rather easy. Now, as I said, those dimensions on that wood shear pin are specific for the size of windmill. In other words, it has to be a certain width and depth. So if you're able to rip a 2x4 and make it that size, then just drilling a couple holes, getting up on the tower, and bolting it in place is fairly simple. And then if it's broken, that means your plunger is sitting on the bottom where it needs to be raised up. And there's a couple fairly simple prescribed practices for being able to measure where the wood rod would bolt onto the plunger rod and lifting that plunger a couple inches, 2 bolts in the hole, and you're done.
Okay. We had one comment back about the concerns with birds, and certainly it would be a consideration where prairie grouse, prairie chickens are located, their leks. These towers could be, they are tall enough to be used as predator perches, and that'd be a planning consideration for someone's or anyone that's in areas where these are birds of concern.
I can see the concern there. We don't address that too much here.
Right.
We know we have grouse in New Mexico, and in some of those same areas where their habitat is a lot of windmill pumping. And to be honest, and not saying that it's not a concern, but it's not something that's an important issue in the western regions that I'm aware of.
Okay. There, from the NRCS, before we do open our lines up for questions, for NRCS folks out there, we do have standards Our pumping plant standard would cover windmills. That'd be Practice Code 533. As you can see from the comments that Craig has made today, there's a lot of application opportunities. I have one raised hand.
Go ahead, caller. You're unmuted.
I was wondering what the best tools that are available for studying the feasibility of using windmills in certain locations. What's the best thing to look at first?
I guess that would be for me, right?
Yeah, Craig.
Whoever wants to answer it.
I guess the important thing is the site itself and knowing that you're going to have adequate wind to deliver the amount of water that you need to be delivered. That raises all kinds of questions. Is it an urban or suburban situation? Do you have a lot of obstructions on the ground or nearby that requires a taller tower? And if so, is a taller tower going to be an issue with neighbors or whatever? So other than that, site considerations, I guess I would say that you want to know approximately or fairly close how much water you want, and then be able to size the windmill to that requirement. In other words, an 8-foot diameter windmill will deliver more than a 6-foot, but less than a 10-foot. So knowing what your need is and the site that you're going to put it on are the two most important things. And that might, too, include a regional, kind of a little bit of a research on how much and what time of year your wind is sufficient.
Okay. So the kind of data the kind of data you're looking for is like wind miles or something?
Yeah, well, just average velocity, and the direction doesn't matter, but average annual or average monthly velocity,
Okay,
and how consistent that is.
Thank you.
Yes, ma'am.
Craig, another note came in and said that Baker's publication, A Field Guide to America's Windmills, is an online PDF, so folks will be able to search and get that online, apparently.
That's great. It's really a very, very valuable resource. I use it all the time. Dr. Baker knew more about windmills than any one man should. He's really a useful book.
And as you mentioned just now, I think you brought up putting windmills up in populated areas. There was a question about zoning requirements, and certainly those would be something that have to be looked at.
Absolutely.
Before erecting a tower.
Yeah, absolutely. I'm sure that if you're within a municipal or city limits, there could be restrictions on it. And if you're outside of city limits, then you've got neighbors to worry about and that sort of thing. So I don't think you just put one up because you want to without checking it out first. We've got windmills here in Las Cruces within the city limits that are there, have been there forever, probably grandfathered in. Nobody's going to mess with them. But to put one up new, I think there would have to be certain licenses required or something.
Certainly. Craig, we've got another question about manufacturers of the pumps.
Yes, sir.
Where are they? Who are they?
The main one and really the principal supplier of the cylinder pumps is Midland Pumps out of, actually they're not in Midland, Fort Worth, Texas, I believe. Yeah. Midland Pumps, and I suppose there are others, but that's the premier pump manufacturer. Very reliable. I pulled a pump not long, it's a Midland pump, pulled it out of a well not long ago that we are pretty certain has not been touched in 70 years, 70. And pulled it out, and it's clean, little cleaning, little tender loving care of it, and it's perfectly fine. Midland Pump is just about the best act in town.
Okay. Any other questions? We had one, another note came in about the online resource, and I'll repeat it again. It was a field guide to American windmills. It was a PDF version that's online by T. Lindsay Baker.
Just a reminder, if you'd like to ask a question, you can dial *1.
Mike, I might say that the one that's mentioned as being an online is not the technical guide. A Field Guide to American Windmills is one of Baker's other publications.
Thank you, Craig.
That's another publication from Dr. Baker. The one that has the comprehensive technical information is entitled The 702 Windmill.
Thank you for that clarification.
Okay. Yeah, he was rather prolific author, but the one that's the most, that's sort of the manual is entitled The 702 Windmill. That's the one that you want to look for.
Great. Thank you, Craig. Doesn't seem to be any other questions coming in. Again, thank you, Craig Runyon, for taking your time. Everyone should have their. We got one more. Do you have favorite brands for towers or motor manufacturers, Craig?
Well, actually, yes. There's only one completely made U.S. windmill left, where there used to be hundreds. There's the Air Motor Company, AERMOTOR, Air Motor Company is the only U.S. manufacturer of windmills today. And as a result, then I have a bias. You can get some foreign-made windmills. They make them out of India, out of China, out of South America. There are a lot of windmills available on the American market today, but there's only one U.S.-made windmill, and that's the one we deal with. It also happens to be convenient that they supply parts and materials for their windmills from 100 years ago. So for old windmills, they're completely rebuildable, and you can rebuild them into like new condition. With Air Motor Company, if you want to save money, then go with one of the Chinese models.
Thank you, Craig.
We have one more question on the line. Go ahead, caller. Your line is open.
I had a question about comparing O&M costs of the windmills to a solar pump system. Could you address that, please?
Yes, I will. Annual maintenance for a windmill includes 2 quarts of oil and occasionally about $10 worth of plunger leathers. The seal on the plunger and check valve need to be replaced periodically. So for something less than $20 a year is about all the maintenance that's required on the windmill, and of course your time and labor. The solar pumps, it's variable because of water quality for one thing, and if you've got pump issues because of sand, then those costs can be a lot more substantial. To be honest, I don't have a firm handle on maintenance costs, but if everything's going well with solar, assuming you're not having any problems, there should be no maintenance costs. I hope that answers your question.
We have no more questions coming in our note box. And with that, Craig, I thank you again for your time this afternoon.
Yes, sir. My pleasure.
It's been very informative. Emily, thank you. This concludes our webinar for the day.